Alrighty, guys. Are we all here? Can you hear me? All right. So I propose we do a few more examples of these radical derivatives, and then we give the proof of existence of these conditional expectations. So let's do one more. Let's do two more examples. So we looked at the one period binomial. This is where we had our psi. We'll go from it was heads and tails, right? And it will take values into u and v. And so, and we had the probability that it will be up. That would be p. Right, so that was the probability of heads. And then we would have that the probability of tails would be the probability that we will go down. This would be 1 minus p, right? And we also had, whereas we constructed the meshes p tilde. So that was the one when you wanted to be going up, you will get p tilde, and there was some formula. There was some formula for this thing. This would be 1 minus p tilde. So we could ask the same question here, right? So if I'm taking, there should be a radical derivative. So what is dp tilde dp? But it's a random variable. It integrates to 1. Okay, so we would on that. It's non-negative. So it's non-negative, and if I compute the expectation, I'm going to get 1. But what is it? Well, let's work out what the definition is. So by definition, of this radical derivative, we will have that p tilde, so that's the thing on top. P tilde of a is equal to the integral over a of this radical derivative. So keep in mind, it's this ratio here. This is a single random variable. So it's not like you cannot break these two into two pieces. This is one quantity. It's not like a ratio of two things. This is just a notation that is being used for radical derivatives. So this is one quantity. You cannot just say that this is the dq tilde and then you can start multiplying and dividing by dp. This is not how it goes. This here is one quantity. It's the notation for the radical derivative. So what kind of sets would we be interested in? Well, we have a very simple structure. So I will look at so I looked at p tilde of it's a very simple structure, right? So we only have h and t. So if we look at it at h, right, then that would be on one hand an integral over that single point h, and then the radical derivative dp. Right, so we're integrating over a singleton. That's just going to be dp tilde dp evaluated at h times the probability of the set h. Okay, so now we know on the left-hand side, p tilde of h, this was heads, this is when psi is u, so this here is equal to p tilde. And then on the right-hand side, On the right-hand side, this is dp tilde dp evaluated at that point h. Times the probability, but now on the p of h, well, h is when the random variable psi is u, so this is going to be p. Right, so this here is the same thing as saying that dp tilde dp at h is equal to the ratio p tilde divided by p. Likewise, if we were to figure out what the random variable is, not at h, but at t, how would we do that? We do that likewise. If I am to look at the probability under the tilde measure of tails, well, by definition of the radical derivative, it means that I should be integrating t here, and then I should be having dp tilde dp, and then dp. So I can work out what the left-hand side is, what the right-hand side is. The right-hand side is, I'm integrating over a singleton. So this is going to be the integrand evaluated at the singleton times the probability of that set, and we know what that is. The probability of tails, this is 1 minus p. And likewise over here, the probability under the tilde measure of tails, this is 1 minus p tilde. And then we solve, we get that dp tilde, the random derivative evaluated at tails, this is equal to, this would be multiplication, so this is equal to, I'll move over, we get 1 minus p tilde divided by 1 minus p. So that's the example of the one period polynomial model, but phrased using the random derivative. Are there any questions on this?
Sorry, why is the expectation of dp tilde and dp equal to 1?
Yeah, good question. That's this one here, right?
Yeah, that part exactly.
So let's try to do it just in this example. So sometimes I call this for, you'll see that in my notes, this is called like a sanity check. It never hurts to do a sanity check. If I am to compute, the expectation of this random variable dp tilde dp, like how would I do this stuff? Well, in this particular case, it takes only 2 values. So I split my omega, split it into two disjoint sets. So I'll split it into h and into t. So what I'll do is I'll look at what's the value of the random derivative on h. Okay, so that's the first part. Times the probability, and now we are on the p over here. So this is times p plus, and then I take the random derivative, and on the other side is t, times the probability of that other set. And again, I am on the p, so there's no tildes going on these guys. Okay, so now what we get is we plug in what it was we just got created. Right, so this was p tilde divided by p times p plus, and it was 1 minus p tilde, 1 minus p times 1 minus p. And now you see all the stuff cancels out. P's and p's and 1 minus p and 1 minus p. I have p tilde plus 1 minus p tilde. I'm going to end up with 1. So that's one way to see it. More general, so not just in this example, but at least in this example, we get the right result. More generally, if we look at, more generally, if I look at the probability of omega, right, I want to get a 1 here, because it's a probability measure after all. And I can use the formula. This is the random Nicolet derivative. How is it related to the probability measure? Well, it'll be an integral over that set. And then you integrate the random Nicolet derivative with respect to the measure. And this is exactly the expectation under that measure of dp tilde dp. Right, and then you go all the way to the left. See what I want.
Oh, so in this case, we're kind of going like backwards with the proof.
Yeah, I mean, this is more general, right? We're done. Right. We looked, so your question, right, in the particular example, here was one way to see the 1 y is equal to 1. But the property holds, it always holds for all random Nicolet derivatives. They always have to have expectation 1. And the reason is that I want a new measure here. So in particular, when I put in omega into that new measure, I'm going to get 1, right? And that's exactly this expectation of this dp tilde dp. So if I want p tilde to be a probability measure, its random Nicolet derivative, it's got to be 1 in expectation. Does that make sense?
Yeah, that makes sense. Thank you.
More questions or comments? I have one more example. So this type of calculation we saw here, this is something that is related to the binomial model. And this is in sharp contrast to some of the stuff that we discussed earlier, right? Here we indeed are integrating over a set that just has this 1 point. But all the way back up until the very beginning of today's lecture, we had discussions about these sets that just had 1 point, and we were in trouble. Right? So here we have sets of that sort, and this has probability 0. Right? But there's a big difference between being normal and having a density, and then being one of these random variables used in the binomial model, where indeed mass is allocated to the singletons. Right? So here there's no density. Just one thing to keep in mind. So this was one more example about random Nicolet derivative. The last example I want to give is something that comes up very, very often in continuous time models. This is behind black shoals. This is something you will see multiple times as part of continuous time finite material. So here is this example here. This is versions of black shoals. So what you do is you take a random variable. You take x. X goes from omega into r, and you make the assumption that x is standard normal. And then we have a standard normal, I cannot use it. I can't use it as a random derivative, right? Because it takes both positive and negative values. So what I do is I look at, we're going to define a new measure. Let's call it Q tilde by the random derivative. So I'm going to define a new measure. And I'm going to define it using this random variable x up here. And the way I'm going to do it is I'm going to exponentiate it. I'm going to put ex up here. But now I need to make sure, so now it's positive, right? This guy here is positive. Exponential of something is positive. So I also need to make sure that it has this expectation 1 that Sherry was mentioning. So, and this thing here doesn't have expectation 1. So we need to recall the moment generating function. For the normal. So if I am to compute an expectation of e to the tx, we need to remember how to do that. And does anybody remember how to do this? Yeah, we integrate. Okay, so that always works. So we can integrate 1 over root 2 pi integral over r e to the tx, and then we need this e to the minus 1/2 x squared and dx. How do we plow ahead from here? It's not too far away from some of the stuff you've seen in the homework. Yeah, Patel says complete the square. So can I complete the square? I can try. It's always something with minus 1/2. You're going to get something else up here, and then you're going to have x minus. You're going to have x minus something. It's probably a t, and then a square. Just make a sanity check over here on the left-hand side of the paper. Something like that. What would we get here? This is minus 1/2 times x squared and t squared minus 2xt. So this is minus 1/2 x squared t squared plus xt. And that's good because this is exactly the one that I wanted here. Right, so there's a price to be paid. If I want to write this here as 1 over root 2 pi, following integral. And then if I want to put e to the minus 1/2 x minus t squared. If I want this equality sign to be true, I need to do a little correction. There's something here with 1/2 times a t squared. This one here has a minus 1/2 of that, so I need a plus. So that goes in there. And now I do integration by substitution. I substitute x with x prime. I'm going to get that this is what I have here. So this was just you can try something that so just to maybe test yourself. Try to do the same. Try to compute e of tx squared. This is called the chi-squared. The chi-squared distribution. This letter there is called a chi. This one here is the chi-square. When you take a normal, you square it, you're going to get the chi-square distribution. So if you're not familiar with a calculation of this sort here, where you complete the square and move ahead, maybe try to do it for the square and see if you can get that to work. Anyway, now we know what the moment generating function is. So in particular, if I evaluate the moment generating function at t equal to 1, if I put a t equal to 1 here, I'm going to get e to the half. Right, so this thing here in expectation has e exponential of a half. So I need to correct that, and I do that by subtracting half here. So this here is a valid radical derivative. It's positive, and it has expectation. It has expectation equal to 1. This is, so now we have a new measure. The new measure is, if you want to know what the probability is of something, so under Q, we need to compute. Q of A. We do that simply by integrating e to the x minus 1/2 over A dp, or more generally, I should say, and more generally, if I am interested in computing the expectation, but under Q of, say, of a random variable y, then I would do that by computing the expectation, not under Q, but I would do that by computing the expectation on the P, and then I would have the random Nicolet derivative getting multiplied out. And the proof of this, it goes through the usual. You start out, step 1, you're going to take y's simple. You take y is simple. So that's an indicator for a set A. You plug it in on the left-hand side, you're going to get Q of the set A. And on the right-hand side, you're going to get E of 1A dq dp. But you know that that's true because that's how we define the different derivatives. Second step, you take y to be finite sums of these yi indicators for ai. And then the third step, take limits, and so on. So you're going to get something like this. So the way to compute expectations on the measures, when you know what the Nicolet derivative is, you just compute expectation on the original measure and multiply it on. Right, so here, in our particular example, this would be compute the expectation of y, and then you have e to the x minus 1/2 x, minus 1/2. This is in the this is in our example. Right, this one here, this is in general. So what you're going to see is pricing derivatives. Right, this is like puts and calls. So pricing derivatives, puts and calls, this will require you to find or construct these random Nicolet derivatives. So often, the name of the game is you can encode the entire model into the Radon-Nicolin derivative. And sometimes people refer to that as martingale modeling. Okay, so I think, do we have questions at this point? Questions about Radon-Nicolin derivatives? We're going to be seeing them a lot in in what follows. So if you start out with one measure, the typical recipe for creating new measures is if you start out with a p, so you know under p, you know that this is standard normal, right? So right, that thing here, this here means that the probability that I'm less than x, that random variable is less than x, can be found by computing an integral, exponential of minus y squared over 2 dy. Right, so that's the starting point. You start out with a probability measure p, and so based upon that, you want to create new probabilities. Based upon that, you want to create new probabilities, and the way that we're going to be doing that is by specifying these random variables that are non-negative and integrate to 1. I mean, there are lots of other things that are encoded in these Radon-Nicolin derivatives. For example, you could ask questions like say Q is absolutely continuous with respect to P, and write dq to P as the Radon-Nicolin derivative. Basic question could be, the question, when is Q actually equivalent to P? That is, not only is Q absolutely continuous with respect to P, but P is also absolutely continuous with respect to Q. And so that is, when is P absolutely continuous with respect to Q? Just to give you an idea about that, you can answer these questions in terms of the Radon-Nicolin derivative. Any guesses on when do we have equivalence? Right. Well, the Nicolin theorem says that Q is absolutely continuous with respect to P if and only if you can find a random variable taking non-negative values, and then you have the formula. So you're given one of those, and you want to know, can I express not only Q being absolutely continuous with respect to P in terms of the Radon-Nicolin derivative, but also that P has the same property? Well, when could this fail? So when could we have when could we have that Q of A would be 0 but P of A will be strictly positive. We could start out by writing out what this here is. This is an integral over A of this dq dp. So when could we have 0 here, but this thing could be positive? So I'm looking for a set here that has positive mass, but I'm looking for it such that the integral here would be 0. Yeah, look at something. Look at the previous example. This is true. The previous example has that. Say that the probability that dq dp, that random variable, is 0. Say that that is positive. And we had exactly that in that counterexample. Good point. That old one here. Here was my Radhanicum derivative. Right? That has a 0. As soon as the random quantity is negative. Right? So on the P, this is normal. So there are lots of 0 probabilities here. And what you get when you do that, so this here was like, like in number 16. Then what happens is that P of A, well, that's going to be positive, but what is the integral? I'm integrating over that set. This is my A. I'm integrating over this set that has positive probability, but what's the integrand on that set? Then Q on that set A is equal to an integral over A, and the integrand is 0. So I get 0. So when are the equivalent? Well, they are equivalent if and only if the probability that dq dp is strictly positive is 1. We could also ask questions like if the probability is 1, well then what is so the equivalent? Then if I wanted to swap them here, what would this Radhanicum be? How would I calculate? So now the equivalent, so that means that P has a Radhanicum derivative as well. How would I integrate? What would I need the PQ to be if I know what dq to P is? Right, I'm hunting something here. That allows me to write the probability of a set A as an integral over A of dp dq, and then here I need dq. I'm trying to figure out what should I put here so this formula is true. What radical negative derivative? What do we think the radical negative derivative should be? Right, so you're given now that we are in this world where it's strictly positive. dq to p is strictly positive. This is for any set A. Say A. Yeah, maybe I'm confusing you. Let me try to write it out. But this is the thing that we want. This is the thing that we want, and we have that q of A is equal to an integral over A dq dp. And so if I take this formula and I plug it in here, so we want this dp dq such that when I integrate dp dq, I get what's on the left hand side, and when I plug in what d here is, this is going to be, that was the thing we're talking about, you multiply onto the radical derivative dq dp times dp. So how do I make this equality sign true? Well, you set dp dq to be, you have to eat out this term there. So you set this to be 1 over dq dp. Right, then this becomes the integral over A dp, which is p. But of course, you can only do this. You can only do this provided that you don't divide by 0. I cannot do this. This could be 0, like in the case of here. Okay, so there are a lot more things to these radical derivatives than just what we talked about. Here were a few more. You can encode equivalences. So in the Black-Scholes model, you actually have equivalence. This thing here is not just non-negative. This is actually strictly positive. So you have equivalence between Q and P in the Black-Scholes model. And the same thing is true in the binomial model that we let's start here. Page 17. The multivariate binomial model we had, the same thing is going to be true there. We had our radical derivative was given as p tilde over p. This is also strictly positive. The same thing over here, the radical derivative on the other element. This is also strictly positive. So again, you will have that the measures in the binomial model, they are equivalent. Alrighty, any other questions or comments before we do the final bit on the existence part? So the existence is going to come straight from Radical theorem. So this is about existence. Existence of this conditional expectation x given g. So the first step is to assume, as we've done before, assume that x is non-negative, and we need to assume that there is an expectation which is finite. Okay, so then you define, we're going to go through these meshes. You're going to define a new measure, G, Q, and GP. And this is going to be defined as, so now x is positive. I'm going to add 1 to make it strictly positive. And then I divide by its expectation. So this here is strictly positive. The expectation of the thing is 1. And so by what we had, we're going to have equivalence between the two meshes. Strictly positive rather negative derivative, that's going to produce an equivalent measure. So that was step number 4. That was step number 1. Now, based upon this, we're going to create 2 new measures. Each defined on this sub sigma algebra. That's the one we're trying to compute the conditional expectation. We're trying to guarantee the existence of this thing, but we're going to guarantee the existence on a smaller one, right? So this one here, that's what we're going to define on F, this measure here. So we're going to create these 2 new measures, and the way that we're going to do it is simply by saying that Q tilde on a set A, this is going to be nothing else than Q up here on that set A, and P tilde on the set A is going to be nothing else than P on A. And this is for A in G. So what I'm doing is I'm taking the 2 measures P and Q and I'm just restricting them. Instead of having them live on F, I'm having them live on G. But in particular, because they're equivalent on the big one, they're also going to be equivalent on the smaller one. So P tilde is equivalent to Q tilde on G. And this is because P tilde is equivalent to Q on F, and G is inside F. So then I use Radon-Nikodym's theorem. So by Radon-Nikodym, we can find a Z, which is G measurable. We find Z, which is G measurable. Because I have equivalence, I can also say that I can say that Z is strictly positive. So the probability under the P tilde measure, this is of being strictly positive, this is 1. The expectation of Z is 1. And it has this Radon-Nikodym derivative property, namely that if I measure Q tilde on a set A, I'm going to get exactly the same thing as when I integrate the random variable over A. Okay, so this is where we use Radon-Nikodym's theorem, which says that if I have 2 equivalent meshes on some sigma algebra, I can find this Radon-Nikodym derivative, strictly positive, integrates to 1, and I can express probabilities in terms of integration with respect to the other measure. Like, so this is Z here. This is going to be my conditional expectation. That is going to be the known thing that lives up here. Okay, so how do I prove that? How do I prove that this z that comes out of this abstract radionuclidim result, that this is exactly this conditional expectation that sits up here? Well, it doesn't take too much work. It takes a little bit of work, but let me carry out the calculations. So what do we have? We have q tilde. We have q tilde. This is a q tilde on the set A. Q tilde on the set A. So this is just that formula, the radionuclidim derivative. This works for any A and G. By the when you view P tilde and Q tilde as measures on G, you're going to get this formula for all G's. Okay. So on one hand, I know, what do I know? I know that Q tilde and Q are the same. Q tilde and Q are the same on G, so I can write here Q of A. And then I'll just break out the two calculations. On one hand, I'll use the radionuclidim derivative that we just created. So this was A, Z, and then it was dP tilde. And now on the other hand, this Q of A, we also have a formula for. This Q of A, we also have a formula for. This is an integral over A, and then it's this x plus 1 divided by the expectation of x plus 1. But now we integrate with respect to what's downstairs. This is dP. And of course, we can simplify this. This is a constant. You can go outside. You get 1 over the expectation of x. And then we get the integral over A of x plus 1 dP. So we're getting closer. We can simplify up a little bit. We can move this expectation here to the other side. So this here will give me that if I move the expectation to the other side, this is ex plus 1. Then I'll have an integral over A, and I'll have my z, and I'll have dP tilde. So this is apparently the same as an integral over A over x plus 1 dP. And this is true for any set A in G. So we're very close, right? Because remember the property that we want. We want the conditional expectation to be a given random variable that has the property that 1, is measurable with respect to the right filtration, and 2, when you do the integral over subsets of that sigma algebra, you're going to get the right thing. So let me just remind you of that property. Right? We have two properties we're hunting. On one hand, it has to be G measurable, and on the other hand, it satisfies this property here for any subset inside that thing we condition on. So I'm hunting such a random variable, and what I'm claiming is that that random variable Z that I'm working with here is going to do the trick. And you can see that it already has the measurability property. What I need to establish is that it has the second property as well. And I'm getting that now because you see what's here is A and Z. A is in G, Z is G measurable. And P tilde, this quantity here, this is going to be equal to the integral over A of Z, but then integrate with respect to P. This is because this thing here, this is because P is equal to P tilde on G. And A is a set in G, and Z is G measurable. I remember the way we could, excuse me, the way that we created this P tilde was by saying that P and P tilde, they agree on G. So here, everything is G measurable. I can have a choice. I can either write P or I can write P tilde. But then I'm home free because I can now simplify. I have p here, I have p here. I can move the 1 to the other side. This is going to allow me to write. This is going to allow me to write an interval over a, and then the expectation of x plus 1 times z minus 1 dp. This is equal to the integral over a of x dp. In this object in here, this is going to be, so that equality is going to be true for any set. And this quantity here, this is g measurable. All right, so the conditional expectation of x given g, this is really nothing else than what I have in there. So this is how, I mean, all the hard work is coming here at the bottom. This is this random result that says that if I have two meshes and the equivalent, I can find a strictly positive random variable such that a bunch of things hold, and it's this z, which is very close. I mean, there's just a little correction with some constants that's going to get that's going to give you the conditional expectation, right? And then, given you have that, then the second step is to say that for x going from omega to r, with the expectation of the absolute value being finite, we write x as x plus minus x minus. Right, and now we have two positive random variables that have finite expectation. And then the conditional expectation of x plus given g, and the conditional expectation of x minus given g exists by 1. Okay, so then if I look at the difference, then this guy, the difference, this is exactly this conditional expectation. So that's how you get, this is how you get the conditional expectation to work under the assumption that the random variable that you're working with, well, it has to be measurable, and then it has to have finite expectation. When you take absolute value, it has to be integral. So I know this last part here, this is perhaps a bit, this is a bit abstract, where we use a very deep theorem from measurement integration theorem, measurement integration theory, to produce these conditional expectations. But so now what we have is we guarantee the existence of a random variable that that we can call this conditional expectation. There's exactly one, and provided that x is integrable, there's exactly one, and this will allow us to do a bunch of things. So, for example, it would allow us. So now we have this conditional expectation, and martingales. Can be formed, right? So we haven't talked about martingales, but martingales to a large extent we have had discussions that say that for a sequence of random variables, we can look at Fn to be the sigma algebra that the first one. So if I call them, well, let's call them in. I call them stock prices. I can look at the sigma algebra that the first n generates. This could be, example could be like, if I take S0 to be 1, I take Sn plus 1, this is equal to, by definition, Sn, and then I take this psi n plus 1. This is our multi-period binomial model. This sequence, psi n, the IID conflicts. If I take such a thing, and then I'll form the stock prices. So every time in my tree, I can go up, I can go down, I can go up, I can go down, and so on. Then I'll get my stock prices, and as I move on, there'll be more and more possible stock prices. I'm looking at the filtration that is being generated by the stock price over time. And I can consider, now I can take, what we can do now is we can take a random variable. So for x, x integrable, we can form this conditional expectation of x given Fn. So these Fn's, here, the increasing, right? I get Fn is less than Fn plus 1, and so on. My x is f measurable, where f is the smallest sigma algebra that makes all these conflicts measurable. Psi 1, psi 2. So I can create myself this system of sigma algebras, and I can now talk about the conditional expectation given one of them. And this is the prototype example of a martingale. It is even so famous that it has a name. You called Levy martingales. So you see, as soon as we got the conditional expectation defined, martingales became just around the corner. Martingales, this is what quantitative finance is all about. So it might very well be that what we just did with these Wernickean derivatives, this seems fairly abstract, and it is. This is not easy material at all. But given that we went through it, we really get benefits out of it. We can now immediately move on and start talking about martingales. And that's the tool that we need. This is the main tool for math finance. And now we have it. We have a little bit of time left, like 15 minutes left. Are there questions up to this point?
Will we be learning more about martingales for the next class?
Yes, yeah. I mean, martingales are it's everywhere.
All right.
Let me just see if I can find my textbook somewhere. Yeah. Let me do this one here. So martingales are absolutely everywhere. If I go down here and look at general expectations in 6.6, I would not be surprised if he starts talking about martingales immediately. Right, and he does. Right, so remember we were working over here in this chapter that was called 2.3 conditional expectations, page 66, and you can see here towards the end of the chapter, he starts talking about martingales. Right, so this comes on. This comes in chapter 2, right? So all the remaining chapters, and there are 10 or 11 chapters in this book, they're all about martingales. So we'll talk a lot more about martingales in this class. You'll talk a lot more about martingales in your next classes. It looks like I'm going to be teaching. Computational finance in the spring semester, and that's the same. There will be lots of martingales everywhere. So here I haven't defined what a martingale is, but you are able to understand now at this point what that conditional expectation is, and this is a prototype. That is the way. This is a main way of creating martingales. Is you take a random variable and you condition on this flow of information you have, and you get this huge class of what's called the martingales. So we don't have the general notion of a martingale yet, but we have the main example. Yeah.
Okay.
Yeah. So next time but every time from now on, we'll be talking about martingales. Are there more questions or comments? Right, so we have a few minutes left, and let me conclude today's lecture with going back and now figuring out how to solve one of these problems we had at the beginning. Find the page. Go back and the example we had here in the beginning, namely this one here. So now we have two random variables. We want to know what this thing here is. So let me show you how to do that. And let's call it quits. So back to the example where you would have two random variables. You would have x and y. It would be multinormal under some measure p. Means are 0. The variance covariance matrix is has 1 on the diagonal, so the variances are equal to 1, and the covariance, or in this case, the correlation. Like there's no difference between correlation and covariance when you have ones on the diagonal. So we want to know what is the conditional expectation of x given y, and we show you how to do that. This is also an old exam problem, if I'm not mistaken. Just find a number. Let's see. How would one go about doing something like this? Well, very often when you work with Gaussians, you want to take advantage of this property that they are independent, even only if the uncorrelated. Right? So x and y are non-independent. Not independent, so we need to do something. Like x and y are not independent, but for Gaussians, for jointly Gaussians, jointly normals, but jointly, we know that independence, this is equivalent to 0 covariance. So here they don't have that, right? Because there's this row that's messing us up. But, so if you look at, so I'm going to call this for y perpendicular. Y perpendicular, I'm going to define this to be x minus rho y. And that's also going to be Gaussian. This is also going to be Gaussian. This is going to be Gaussian. It's going to have a 0 mean. What's the variance going to be? I'll have to look at the variance of y perpendicular. Well, it's equal to the variance, so it'll be the expectation of x minus rho y squared, because it has 0 mean, so no need to subtract a mean here. We'll get that this is the expectation of x squared plus rho squared, the expectation of y squared, and then minus 2 rho, and then the expectation of x, y. So this here is equal to 1. And this one is equal to rho squared times 1. Right, that's why we're using the diagonal elements. The expectation of the product, this is where we're outside the diagonal element. So we get minus 2 rho, and then this will be another rho that will give me a rho squared. And so I'll be left here with 1 minus rho squared. So that's the variance. So I'll put that up here. So I have a Gaussian random variable. This is my perpendicular guy. And he has a nifty feature. He has the property that if I look at the covariance between y and y perpendicular, I would get, what do I get? This would be the expectation. So again, there's no mean here, so this will be the expectation of y perpendicular. Like this is the covariance. Covariance is just the expectation of the product. I'll plug in what this y perpendicular is. This is y times, I'll plug in what the perpendicular is. This is x minus rho y. And this here is the expectation of xy, this was rho, minus the expectation of y squared times rho, so this is 0. And so because y and y perpendicular, they are jointly normal, and this is because y perpendicular is a linear combination of jointly normals. Right, so we have gotten ourselves created a random variable y perpendicular, which is uncorrelated with y, and furthermore, y and y perpendicular are jointly normal. Okay, so then you know this is going to imply that y and y perpendicular, they are independent. Okay, so let's do that one more time. Right, my original random variables, my x and my y out here, they had zero mean. That was the assumption we started out with. But they are not independent because there's a row sitting on the off-diagonal elements. So x and y are not independent. So what we do is we change y a little bit. We're going to change y a little bit and call it y perpendicular. And the way we're going to change this is according to this formula. Now, because x and y are jointly normal, so I take a linear combination of jointly normals, I'm going to stay within that family. And so y perpendicular is going to be jointly normal with x, and it's going to be jointly normal with y. And when we work out what the correlation is between y perpendicular and y, we're going to get a 0. Right? So this is why the notation is the way that it is. This y perpendicular seems to indicate that this is independent of y, and that's exactly true because you have no correlation and you're jointly normal. And so that's what we need to compute this expectation of here. So this conditional expectation of x given y, how would I write it? Well, I would just plug it in now. I would say what is x? I use the formula. This is the expectation, and then what? I'll move this part to the other side. I'll get that this is y perpendicular plus rho y given y. Okay, so now what would this be? Well, go back to these two extreme situations that we had, namely, the first one is we'll use this conditional expectation, better be linear, so it makes sense, then we can just use linearity. Okay, so this is a constant, you can travel outside. So we would have that. Okay, so keep in mind now, y and y perpendicular are independent. So we're thinking about this as being our best estimate. This is going to be our best estimate of y perpendicular given that we know y. But y and y perpendicular are independent. Okay, so we would imagine that the conditional expectation is simply the unconditional one. Right, so here we're using that y perpendicular is independent of y. And over here, my best estimate of y, given that I know y, well, that's going to be rho y. And so we're also using here that y is sigma y measurable. Okay, so there's a little bit here to be proven, namely that if I compute a conditional expectation of an independent random variable, I should just get the unconditional expectation. So there's something to be proven here. There's also something to be proven here, namely that if I am already measurable, then I'll get y. But this is plausible, right? Because that y here is already sigma y measurable, so he can serve as the conditional expectation. Regardless, the expectation of y perpendicular, we figured out what that was on the previous slide. That was the 0. And so we end up here with nothing else than rho y. And that's the answer. So it's true that the concept that we're working with is quite abstract. But if we put it into a setting, like a jointly normal setting, it becomes very specific. Like, what is the conditional expectation of one Gaussian given a correlated Gaussian? Well, we're going to get that. And here you can also see that this conditional expectation, this is really a random variable. This is a constant times a random variable. Which this conditional expectation here, this is yet again a random variable. Okay. We are out of time. That being said, are there any questions before we call it quits? If not, I just want to remind you guys that we have office hours on Thursday and Friday morning, and there is a problem session tomorrow morning with which are, oh, there was a question in the chat. What is y perpendicular? So the definition of y perpendicular is, it's right here, right? This is a random variable, and you get that random variable by taking x and subtracting away rho times y. So that's going to be yet another random variable, and figure out what a distribution is. But that's not the, that's just one part of the puzzle. The key part of the puzzle with y perpendicular is that it has this this property that when I look at how it covaries with y, I get independence. That's the key thing, because it's that's the key thing that allow me to throw away this conditional part, throw away this one here, and just do the unconditional. Yeah. More questions or comments? All right, then I'm going to call it quits, and I'll see some of you guys on Thursday and Friday mornings, and I'll see the rest of you next Tuesday.
Thank you, Professor.
Take care.